So, here comes the last lecture of the 4th week. You must be wondering, why should I bother about talking about arc length? That is, if I have a curve, a path CT, which is described by say 3 functions, that is it starts from some, so here is the interval AB and t is something in between, not time, and this is C of A, the end point of the curve, and the C of B, the other end point of the curve. So, if I call these end points A and B, what is the length of the curve AB? Is this question meaningful? Why you want to know the length? Or just because you have to do some math you want to know the length? Does it have any physical significance? It is, because if I know the velocity vector at every point and I know I have travelled from CA to CB and I know that how much time has elapsed, I should be able to know what is the distance I have gone. So, it is a very natural question of asking the distance one has travelled. So, distance is speed into time, that is what we learn in our basic school physics, but what how do I really use that idea here, because the velocity is changing at every point. Suppose I am looking at a curve, I am now, instead of looking at just this kind of very general kind of stuff, let me look at a physical stuff where t would now represent time and a particle moves from a point A to a point B in space, and I am observing its motion from A to B, and this corresponds to the time t0 where it starts. Rt0 is the radius vector at time t0 to Rt1 where it stops. So, Rt of course is given by xt, yt, zt as before. Now, question is, what is the length of AB? That is what I am interested in. How would I find? So, you might say, okay, here I know that r dash t is velocity at every point t, and then velocity into the time taken, the t minus t0 could be the length. Not a bad idea. So, how would I use this idea of that distance is velocity into time? How will I use this idea? And here exactly the whole idea of calculus, which is sometimes this notion of infinity principle, which has been recently mentioned in a book called Infinite Powers, the story of calculus by Steve Strogatz, a beautifully written book, wonderful, and there he had actually told how things really occur, how calculus is used. So, what how does one really find? So, here is a curve with the starting point Rt0 and end. So, this is the way particle has moved. So, how will I find the length? The idea is divide the whole curve traced by the particle into small parts and join them, those little parts, by straight lines, those partitioning points by straight lines. So if you magnify this zone, so it's like this, so I am taking these curves, taking these partitioning points, so here I am joining by straight lines. So it's a kind of magnification. So what is happening between, suppose here it is RT and here it is R, just a little off from T plus delta T. So so here suppose this point is, the vector is RT, and here the vector is R of T plus delta T. We assume that the velocity that you have at every point here remains unchanged. When delta t is very small, when you move from this point to this point, the velocity remains unchanged. The position changes a little, the velocity remains unchanged. In a very small interval of time, my infinitesimally small interval of time, very, very small, very near zero, we assume that the velocity remains unchanged. So basically then, to cover this distance, that is to cover delta RT, this is the vector delta RT, which is the difference of these two vectors. This vector plus this vector is this vector. RT plus delta RT is R. So this delta RT, to cover this distance delta RT, you take, and the time has elapsed from T to delta T, the time elapsed as delta T, you take this amount of time. So this is on one arc length. Similarly, you can do it on every arc length, every partition. Okay. So basically you divide the time interval into small partitions, and at those time intervals, so at T plus delta T you take R of T plus delta T. So you believe that we assume that between T and T plus delta T the velocity doesn't changes. This is the velocity, and this is the distance that it travels along the straight line between. So this is the distance. Because these 2 points, it is magnified, are actually so close on the curve that this curve is very well approximated by the straight line. So you can understand, if we do this kind of, for every such small intervals, and we keep on reducing the delta t size, so I will have more and more numerous points on this curve, and as more and more numerous points, that is, you have more points, you will have more straight lines, and more the straight lines are, the better you approximate the curve. More points you have, the better these little straight lines approximate the curve. So in the limiting position, you will finally get the length of the curve. So this delta t is approximation of this little length, this little arc length. So as you have more and more points, those delta t's, and you sum them up, those will be more and more near to the length of this curve. So basically what I am telling, r dash t, obviously I have to write in terms of norm, because norm is the speed. So the speed into distance, r dash t is a vector, I cannot write r dash t into delta t, it's meaningless. So I have to write norm of r dash t. Please keep a note of that, it has to be norm of r dash t. So it's speed into time. So when I do such, so I calculate it by every of the step by this and sum them up, and as I keep on increasing my, as I make the time interval smaller, I will have more and more points on the curve, and I will evaluate the distance, I will find the length of the more smaller and smaller straight lines, the smaller and smaller chords, I will keep on finding the lengths of smaller and smaller chords and sum them up. Because as I continue to sum up the smaller and smaller chords, I actually go more near and near to the actual length of the curve, and in the limit I will reach it, and that limit, so the length of the curve is integral from t0 to t1 r dash t dt. This is the length. So if you have a general curve CT, so here, so length, let us write it down finally here. You can understand, because here what we will do, we will sum up all these lengths for every such small chords joining the two partitioning points, which are r of t and r of t plus delta t. More as delta t is smaller, you will have more and more partitioning points on the curve, and more smaller and smaller chords that will sum up, and as we keep on decreasing the delta t, we approximate the length of the curve better and better, and in the limit we will get the length of the curve, which, and hence these sums are nothing but the kind of the sums that you get in the integral. And so this is what, by definition of integral, this is nothing but this integral is simply an integral that you know, integral of a function of time. This norm of r dash t is nothing but a function of time. And so length, as you know, here I would write down here as t0 to t1 so this is how we have applied this very simple fact that distance is time into speed to actually compute the length of a curve, which is actually a curved one, which is actually a curved curve, which is not a straight line, and it's not so simple to compute that. So basically again it is the limiting procedure of calculus, the procedure by which Archimedes found the area of the circle. That same procedure is applied here to find the length of a curve in 3 dimensions. Now you see this whole idea, need not be only about a curve where t is time. It could be any parametrized curve. For example, if I write Ct, suppose I get into n dimensions. See now how we can make a leap in the imagination. Then what is C dot t or C dash t? So let Ct describe a curve where t moves from A to B. So Ca is the start point and Cb is the end point. So C dash t is now x1 dash t. You cannot visualize this curve, but you can algebraically describe it. And that's the power of algebraic description, that geometry, which is beyond our eyes, beyond our vision, can always be given an algebraic description. This interplay between algebra and geometry, a kind of geometry is algebra and algebra is geometry type of this sort of idea that algebra and geometry, they continue to interplay with each other, is one of the most fundamental things in mathematics, and that has to be appreciated if one has to enjoy good mathematics. So in general, the arc length, so what I do is take the norm of C dash t, which is nothing but, if you take the Euclidean norm, which is x dash 1t whole square plus x dash nt. Okay. This norm, and by the definition of the arc length, so basically I want to find the arc length of this curve which has moved from the point Ca and gone to Cb. This arc length is given as integral. So T is A, T to B, A to B, Now for example, let me give a very simple example again using circular motion. So consider a point again moving in a circle. And with its center is at the origin of the axis. As we have seen earlier, and you should get habituated to this description, this parametric description, that this can be, if the magnitude of this is r, that is, and this is fixed because it is a circular path, r cos t, r sin t, and t lies between 0 and 2 pi. So it starts from here and goes along anti-clockwise in this direction. So suppose it is moving in this direction, a particle. So what is the length it traverses first? So let us see, it should traverse the length of the whole circle. So it should be 2 pi r. Let us see whether our arc length idea conforms with this very basic fact that the circumference of a circle is 2 pi r. If it does, then our idea of this, using this speed velocity idea, speed into velocity is the distance idea to find arc length, is actually a good one, and you will see how things work actually. So this arc length here, length L, is 0 to 2 pi root over, the derivative of this is minus r sin t, so minus r sin t whole square plus r cos t whole square dt. So it will, whole thing will become r square sin square t plus r square cos square t. So r square will come out, so it will become 0 to 2 pi sin square t plus cos square t is 1. So it will become r square inside the root, so it will become r and come out r dt, which is 2 pi r. So that is exactly what it is. So if you take a particle moving along a circular path, and if it starts at the point here, so if it starts at the point r0 and it comes back to the point r0, then it has traversed a distance 2 pi r. Suppose it makes n number of rotations, then the length of the path that it travels, so if n rotations are made, n complete rotations are made, then the length is nothing but n into 2 pi r or 2 pi n r. So that is the length of the curve. Okay. So let us just try to do something in 3 dimensions. So here you are using the ideas from a single variable calculus. This is basic integration. Why we have done this? Applied in, we have not spoken about integrals here, but we are using, see, the whole idea in multivariable calculus is that I can use any idea from single variable calculus at any time. So integration for single variable calculus is already known to you, so I am using it here. In the next, after the next week, we will really talk about having talking about multiple integrals, and that would be very different. And so here we first talk about these kind of things. So we are using just one stuff. So let us go back and talk a bit about finding the arc length. So let us take an example from the book. So there is a path defined here in the book. So how do I find the arc length of this, and t is from 0 to pi. So C0, that is cos 0 sin 0 t 0, that is 1 0 0. So, the point here starts from 1 0 0 in the space, in the 3 space, and then goes to a point where it is cos pi, some point, maybe my drawing would be completely wrong, but goes to a point where you have minus 1, sin pi would be 0, and that will be pi. So, goes to something like this. So, now I have to find the length of this curve from A to B. So, how do I find the length? It is again the same story. So, you find C dash t here, which is minus sin t cos t 2t, and the norm of C dash t, sometimes when you describe a path like this, C dash t sometimes is called the velocity, but okay, every time you have t, the parameter t need not be time, only when it is time it is called the velocity. So, you can compute this to be, I am not doing the full calculation, you can do the full calculation. So, the length so it is between 0 to pi, t is between 0 to pi, 2 into root over t square plus half whole square dt. So, there are standard ways to integrate this. Basically, this is nothing but you have to look into the indefinite integrals of the form of x square plus a square. Here x is representing the role of t and a is playing the role of half. So, then you apply that whatever formula you would have, and then you will get an answer. Okay. So, I do not want to get into the details, but finally when it will comes in terms of pi, and I will write down the final answer and ask you to check it, is something approximately this. So, this as given as homework for you to compute. For computing out in details. Now, there is something called the arc length differential. The arc length differential. So, what is an arc length differential, right? So, basically this idea works in many cases. Suppose you have a curve like this going from some point CA to CB, a path described by the curve, the functions CT. Now, I look at a very small part of the arc and ask what is this length of this, which is sometimes written as ds. Please understand, here again look at the curve from, so here there are 2 points. From the origin O, this point is a C of t and this is C of t plus delta t. And this distance is delta C, change in C. And this delta C, delta CT basically, this is nothing but C of t plus delta t minus CT. Now, if delta t is very small, then delta Ct actually coincides, actually is a good approximation of the arc A dash B dash. Now, what is delta Ct? C is given as, so I can write this as x of t plus delta t, y of t plus delta t, z of t plus delta t, minus xt, yt, zt. And this simply says that this is nothing but x into t plus delta t minus y of t plus delta t minus y of t, z of t plus delta t minus z of t, and this is equal to, I can write this symbolically as delta x of t, delta y of t, delta z of t. When this delta t is very small, this delta x, delta y and delta z are also very small, because we are always thinking of a continuous curve. We are not thinking of any very discrete curves. Of course, you can say that there is this famous book, question in the book by Mandelbrot, The Fractal Geometry of Nature. How long is the coastline of Britain? Because if you take a coastline, okay, you will look at a coastal curve, but if you magnify it, you will see that smaller and smaller and smaller curves, almost same, which has the same appearance of the original coastline again appears. You again magnify, so self-similar patterns seems to appear and appear and appear. Then how would you really compute the length as more and more complexities appear? So that gives rise to the whole study of fractal geometry, which we won't do here. Here we are only considering, but fractal geometry is an interesting area which you can just look into later on, but from the net. And here we are talking about smooth and continuous curves, nice curves, but there is no such irregularity. So this is a very calculus deals with regularity, and that's the one of the key ideas that you have to keep in your mind. Calculus is about regular objects. Calculus is not about very rough and irregular stuff. Change in regular objects, that is, regularity is one of the key themes of calculus. So basically, when delta t is very small, then delta Ct represents the arc length, the AB, that is delta S, and so on. So delta S is very well represented by delta Ct. So in that case, when t is very small, we symbolically write delta S as ds and call it the differential of S, differential of the arc length. Then delta x t is written as dxt, delta yt, when delta t is very small, is symbolically written as dyt, and delta zt is symbolically written as dzt. There are a lot of issues in this whole thing which I am not getting into. So basically now what we have written down is that ds t, if you want to keep t here, you can put a t here also. Because the length would depend on the time period, or the t that you are taking. So ds, for example, or if you don't want to put t, if you don't want, doesn't matter. So I will not put t here because you understand. So ds is actually given vectorically represented as dx, dy, dz, which a physicist would always like to write. Physicist. A physicist would always write as dx I vector, dy z vector, dz k vector. So the length, arc length, the differential arc length is given as dx square plus dy square plus dz square. Okay. So this can be again written as root over with the differential of time, this dt multiplying top and bottom by dt square, basically you might think. But basically you first do the operations with delta x, delta t square, delta x, delta t square, you do the operation with delta x, and then when x is time is very small, change them to delta t. That's the way of doing stuff. This is a way of doing stuff. Of course, I can give a much more detailed, elaborate argument here, but which I am not because of time, and you need not get into too much of arguments. Just learn the spirit of it at this moment, because we have been doing, yesterday also we did a kind of good amount of proof using implicit function theorem. So today let us be little heuristic. Sorry, dz. Now what is the length? So if you take the small arc lengths and they add them up, then that is the length. So a length of a curve, another way is it has moved from t1 to t, is summing of this ds. So what is the summing up of this ds? So t0 to t1 dx dt whole square plus dy dt whole square plus dz dt is, you can extend it to n dimensions also. I will leave it to you to do it. So this is t0 to t1 x dash t whole square plus y dash t whole square, basically writing the same thing, z dash, killing time you can say. So whatever the way I had found the arc length by using these small little chords and then summing them up and getting an approximation of the arc length and then keep on decreasing this partitioning size delta t, the same thing I get by finding a differential to the arc length, the same way I get the same answer. So obviously taking very small parts on the arc length itself, so that arc length itself, if I can take a measure of that or length of the curved part and then add them up, I will get the whole curve. So with that idea also I reach the same story. So our whole idea of using this velocity into time business to find arc of a curve actually makes sense. So with this I would like to end today's talk, and tomorrow we will talk about vector fields. You have learnt about vector valued function. F is a vector valued function. It takes from a point in a vector space say Rn and puts in a vector space Rm. Now vector fields are special kind of vector valued function where at least each of the component functions that you will have, because if you are mapping a point in Rn to Rm, then f of x is in Rn, we will have m components and each of these components will depend on the chosen x. So each of these components are a function, components, m components of fx, which is a vector in Rm, is a function from Rn to R. Now each of those functions from Rn to R has to have all their partial derivatives, this has to be differentiable, all their partial derivatives must exist and should be continuous. So that kind of differentiability, that this is the minimum requirement when a vector function would be termed as a vector field. The notion of field is ubiquitous in physics and has a huge application, and till this day the whole of physics moves on the idea of fields, and so it is very important to have an understanding of what is a vector field. And tomorrow's class, on the last lecture of the 4th week, we are going to talk about a vector field. Thank you.